Hi, welcome to lecture 5 on linear programming problems under this course on computational mathematics with Sage Math. In this lecture, we are going to look at solving linear programming problem using simplex method. In the last lecture, we looked at theory behind simplex method and we described what is the simplex method algorithm. So let us start with an example and we will solve this example using this algorithm. So let us start with a problem which is a maximization type subjected to these constraints. So the problem is to maximize 2x1 plus 3x2 plus 3x3 subject to 3x1 plus 2x2 less than equal to 60 minus x1 plus x2 plus 4x3 less than equal to 10, 2x1 minus 2x2 plus 5x3 less than equal to 50, and x1, x2, x3 all are non-negative variables. Now the first step in this simplex algorithm is to convert this problem into a standard linear programming problem, which is a minimization type. All constraints should be equality type, all the right hand side should be non-negative, and all the design variables should also be non-negative. Okay, now in this problem all the right hand sides are already non-negative and all the design variables are also non-negative. Therefore we do not need to make any changes for right hand side and also for the design variables. The objective function in this case is of maximization type, so we need to convert this into minimization type. So instead of maximizing this function, we have to minimize negative of this objective function, and each of this inequality constraint we need to convert into equality constraint. So, and here all these three constraints are less than equal to, therefore we need to add slack variables. So in the first constraint we will add a slack variable x4, in the second constraint we will add a slack variable x5, and in the third constraint we will add a slack variable x6. So the problem in standard form will look like something like this. Okay, minimize minus 2x1 minus 3x2 minus 3x3 plus 0 times x4 plus 0 times x5 plus 0 times x6. These are corresponding to slack variables that we have introduced for each of this less than equal to constraint. And then first constraint will become now 3x1 plus 2x2 plus x4 is equal to 60. Second constraint will become minus x1 plus x2 plus 4x3 plus x5 is equal to 10. Third constraint is 2x1 minus 2x2 plus 5x3 plus x6 is equal to 50. And all these x1 to x6 are non-negative. These x1, x2, x3, x4, x6 are all design variables. Now we have introduced three more variables, x4, x5, x6, which are slack variables. Right. Now how we are going to solve this problem? So first thing we will need, we will create what is called initial simplex table. Now if this is the problem, it is easy to guess that we can take x4 is equal to 60, x5 is equal to 10, and x6 is equal to 50, and x1, x2, x3, 0 will as a basic feasible solution. This basic feasible solution satisfy all the constraints and they are all non-negative, so it is a basic feasible solution. Okay, so to begin with, we can take basic variables as x4, x5, x6. In this case, it is very easy to guess. However, that will not be straightforward in many other cases. We will see it later. Right. So what do we do? So we will create what is called initial simplex table. So let me show you what is this table. So this here in the first column we are writing basic variables, and basic variables to begin with are x4, x5, x6, and this in the simplex table we had reduced cost coefficient, which we have denoted by Cj minus Zj, so that will be the last row, and in this case last row is nothing but this coefficient of x1 to x6, and the last one here is the right hand side, and here it's the value of the objective function for this particular initial basic feasible solution, which is 0 at present. Right, and this Cb is the coefficient of the objective function corresponding to basic variables. So basic variables are x4, x5, x6. So this is 0, 0, 0. And then the first column is x1, that is the coefficient of x1 in these three constraints, right? And then coefficient of x2 in the second column, coefficient of x3 in third column, and so on. This first row, this particular one, the first row represents the value of the coefficient of objective function, which is 9, -2, -3, -3, 0, 0, 0, and so on, right? So this is the what is called initial basic simplex table. Now we need to update this table. At present, the reduced cost coefficient, which are at the bottom, there are negative coefficient. That means this is not an optimal solution. Why? Because in case we bring in one of this basic non-basic variable, for example, let us say x1, then the value of the objective function, which is 0 at present, will reduce to negative. So therefore, there is a chance of reducing the function value or the objective function value further. Therefore, this is not an optimal solution. In case this is optimal solution, we can stop here itself. So in case this would have been all positive coefficients, x2, x3, x4 in the objective function, then this would have been a optimal solution. Okay. Now what we are going to do in order to implement this simplex table in Sage Math, we will not consider this column corresponding to CB, and also we will not consider this column corresponding to ZJ. Remember how we have computed ZJ? ZJ was the dot product of CB with the column corresponding to non-basic variable. So for example, the column corresponding to the non-basic variable here is -2, 3, -1. So you look at this, -3, -1 and 2. So look at this and take the dot product with this CB. So everything, since CB is all 0, the dot product will be 0. That is why you see the row corresponding to ZJ will have all 0 value, right? So and in order to update this, how we are going to update this, let us just look at from this simplex table. So here we are going to consider one which is most negative reduced cost coefficient. So for example, we can take any x3 or x4. So let us see, we'll consider x2. If we consider x2, which will be incoming variable, we need to decide what is outgoing variable. So the incoming variable will be decided by the last row, which is the most negative in this reduced cost coefficient. Now we have to, so suppose x2 is incoming. So let us consider this column. The values here are 2, 1 and -2. And then we have to take the ratio of the right hand side by the positive entry in that particular incoming column. So here we have to take 60 by 2, which is 30, then 10 by 1, which is 10, and 50 by -2 we can't take because this is negative. We have to take only the positive entries in that incoming column. Therefore, the smallest ratio is corresponding to 10 by 1, which corresponds to x5. So x5 becomes outgoing variable and x2 becomes incoming variable. Now, therefore, this x5 will be replaced by x2 in the next simplex table, and in the next simplex table we need to update this particular incoming column. So we'll make the pivot entry, which is this here, which is going to be 1 here, that is corresponding to x5 and x2. So that will become 1. In this case it is already 1, so we do not need to do anything. In case this was not 1, we'll have to divide this whole row by that particular value. Pivot element is what we call. And then this one we have to make 0, then this one also will make 0, and the last entry, which is the corresponding to reduced cost coefficient, that we will also make 0, and that we will apply elementary row operation. So what are the elementary row operation in this case we have to apply? This the row corresponding to x5 we will divide by 1. In this case there is no need of dividing, but then this entry, in order to make 0, we'll have to multiply the second row by 2 and then subtract from the first row, that is the row corresponding to 4. Similarly, for x6, this -2 have to become 0, so that we have to do what? We have to multiply this the row corresponding to x5, pivot row, by -2 and then subtract from the row x6. and that is what exactly again we have to do with corresponding to last row, which is Cj minus Zj. Right. So then in that case, this x5 will have to multiply by minus 3 and subtract from the last row. So that is what we will do. That is elementary row operation, using which we will update this simplex table. Right. Now, just for convenience, since all these the computation that we have done here, Cj minus Zj, can be done using elementary row operation by what is called pivoting. So therefore, there is no need of computing this Zj and Cj minus Zj separately. Rather, we will use elementary row operation. Now, what we are going to do, we will not consider this particular row, the first row in this case, the coefficient that is already known to us, and this also we will not consider, this Cb column, and this Zj also we will not consider. So we will consider only the basic variables x4, x5, x6, that is the 3 row here, and then top one will write as x1, x2, x3, x4, x5, x6, and the right hand side, this right hand side will consider, and the last row, which is the row corresponding to Cj minus Zj. Now, in order to find what will be incoming column, that we will be deciding by looking at whether you have negative reduced cost coefficient. In case all the reduced cost coefficients are non-negative, then you have reached the optimal solution, and we know why that is optimal. Okay, so and then after, once we do that, then we'll have to decide what is in outgoing variable, that is by taking the ratio. So we will create 3 user-defined function. One for once we have decided what is going to be the pivot entry or pivot element, that is the row and the column corresponding to outgoing and incoming variable, then we will pivot. That means we will make that particular pivot entry as 1 and the remaining entries in that column as 0. So that we will name as pivoting. So so let us look at what we are going to do. So first we will create the initial simplex table. So for that purpose, we will write this coefficient matrix A, which will also include the last row corresponding to reduced cost coefficient and also the right hand side. So let us create that 3 functions first. So first is this pivoting, which will do make the pivot element as 1 and the remaining entries in that particular column as 0. So that is this is a program for that. Next, we will create a user defined function to find out what will be the incoming column, that is incoming variable. So for that, we will have to enter what is the coefficient matrix A and the number of variables. How many variables? In this case, the number of variables are 6. Right. So what we are going to do in that case, we will just look at what are the last row. The last row here is going to be the number of rows minus 1. The index will be number of rows minus 1, and look at, in case all are if all are positive, then we don't have to do anything. We would have reached the optimum, right? And otherwise look at which is the most negative, so that this particular code will find one of the most the one which is most negative, right? So let me run this, and then next one is to find out what is the pivot row, that is the one which will decide what is going to be the outgoing variable. And for that, we need to find out the ratio of the right hand side by the incoming, the positive coefficient in the incoming column. So that is why here, if AIQ is positive, then you will consider that ratio and update that ratio in case that ratio which you have computed is smaller than the previous one, right? And in case you do not find anything which is positive in that particular incoming column, then the problem is unbounded. So that's the small simple code here, right? Now let us make use of these 3 user defined functions that we have created. Namely, one we have created as pivoting, second one we have created the one which will find what is the incoming variable, and the third one is the one which will find what is the outgoing variable. Okay, next let us create the initial matrix A with corresponding to this initial basic feasible solution, right? So this is your first row, which is corresponding to the first constraint. This is corresponding to the second constraint. Of course, the right hand side, the value is added at the end, and this is corresponding to the third constraint, and the last one is corresponding to the reduced cost coefficient, which is nothing but the coefficient of the objective function in terms of minimization. Right, so the coefficient of x1 in minimization problem is -2, coefficient of x2 is -3, coefficient of x3 is -3, coefficient of x4 is 0, coefficient of x5 is 0, x6 is 0, and the value of the objective function is 0 at this stage. So that is the matrix A. Right, now we will also add this row and columns which we have written as basic variables, and the variables which are x1, x2, x3, and the last one we will write as RHS. So how do we do that? This is code which will help you to create that simplex table. So first we will create list of variables x1 to x6, and then in that we will also create initial basic variables which are x4, x5 and x6, and then header row will be the basic variables, and the last one is RHS, so we are adding that RHS. Similarly, header column will be the first one we will write as basic variables, that is the label, and then the basic variables, and in that we will append one which is called Cj minus Zj, that is the row corresponding to reduced cost coefficient, and then use the function called table on the list of rows of A, and then give the header row and header column, and then let us see what we get. This is what we get. So that is your initial simplex table which we have created using Sage. Right, so you can see here you have x1, x2, x3, x4, x5, x6. This is the right hand side. These are the basic variables, and this last one is Cj minus Zj, that is reduced cost coefficient. Okay, so we know that this is not going to be at this stage. The basic feasible solution is going to be x4 is equal to 60, x5 is equal to 10, x6 is equal to 50, and x1, x2, x3 which is equal to 0, and this is not optimal because you have negative reduced cost coefficient. So we need to update this simplex table. That means we need to decide what is going to be incoming variable and what is going to be outgoing variable. So we already know, we already computed that the most negative we can take as corresponding to x2, and then we look at the ratio 60 by 2, 30, 10 by 1, which is 10. So this is the smallest. This we don't have to consider because this corresponds to negative yiq. Right, so let us call the function pivot column, which will decide which will be the incoming variable, and in this case the incoming variable is x2, which corresponds to the second column. This corresponds to second column, and the index of the second column will be 1. Right, next we will find out what is going to be outgoing variable. So for that we will be calling pivot row, and we have to give what is A, and then we have to decide which we have to also input what is the incoming column, which was Q, which we obtained in the previous step. So let us call this. In this case it says that x5 is going to be outgoing variable, which corresponds to row number 1, the second row. Right, the x5 corresponds to second row, that is the row numbers and column numbers starts with 0. Right, so once we have found out what is P and what is Q, now the variables, the basic variables at present are x4, x5, x6. Now it will be updated to x4, this will become x2 and x6. So let us update that basic variables. So how do we update basic variables? The pth coefficient or pth entry in the basic variable will be replaced by the qth entry of the variables. Right, so that is what we have. Now if you want, you can look at now what are the basic variables. It has now become x4, x2 and x6. That is what we saw. Now let us do what? Let us pivot A. That means once we have decided PQ, that is the pivot entry, pivot element, in this case P is 1, Q is also 1. So what we have here is, this is my pivot. So we will do the pivoting, and for that purpose we will call this function called pivoting and A comma P comma Q, where PQ is the entries corresponding to incoming and outgoing variables. Right. So now once we have updated this A, then again let us create this simplex table. This will be the first simplex table after updating the initial simplex table. Right, so this is what we get. Right, this is, you can see here, this was the incoming column and this was the pivot entry that has become 1, and the remaining entries in that particular column has become 0. Of course, we could have computed this Zj minus Cj minus Zj using that formula, but it is, easier or simpler to find it using row reduced echelon form. Okay, now let us again look at this. This last row again has negative reduced cost coefficient. Therefore, this again is not a optimal solution. At this stage, value of the objective function is 30, right, which corresponds to the basic feasible solution, which is x2 is equal to 10, x4 is equal to 40, x6 is equal to 70, and x1 equal to 0, x3 is equal to 0, right, and x5 is equal to 0. But that is not optimal because this you have negative coefficient in this reduced cost coefficient. So we will again find out what is the pivot column, what will be the incoming variable. So let us again call this A, comma 6. 6 is the number of variables, and in this case the Q is x1, that is x1 is incoming variable. That is what you can see here. There was only one negative reduced cost coefficient, so the column corresponding to that is x1. Therefore x1 is incoming variable, and the Q value of Q will be 0 because that corresponds to 0th column. Right, next we will decide what is the outgoing variable. So outgoing variable will be decided by taking the ratio. Now in this particular incoming column there is one which is negative corresponding to x2, but there is only one which is positive and the other one is 0. So we'll have to just take the ratio of 40 upon 5, which is 8. That is the smallest because that's only one. Therefore the first x4 will be outgoing variable and x1 is incoming variable. Okay, so once we have decided what is Q, then we will decide what is P, and in this case P, the outgoing variable is x4, which corresponds to P is equal to 0 and Q is also 0. Now if you want, you can print what are P and Q. So if I say P comma Q, they will get 0 comma 0. That is what I said. Right, now let us update again the basic variables. So basic variables, that is the Pth basic variable will be now replaced by the Qth non-basic variables, right? So so let me execute this, and then next step is to again pivot this A. So I call this pivoting P comma A, P comma Q, and then now create the simplex table. When you create the simplex table, this is what you get, right? So now you can see here all the coefficients in the last row, that is reduced cost coefficient, has become non-negative. Therefore this particular solution at this stage is optimal solution. So what is the solution here? Basic feasible solution is x1 is equal to 8, x2 is equal to 18, x3 is 0, x4 is 0, x5 is 0, and x6 is 70. But x6, as you know, this was kind of artificial variable or dummy variable which we introduced. So therefore this does not enter into the solution. So the basic solution is x1 is equal to 8, x2 is equal to 18, and x3 is equal to 0, and the value of the objective function for x1 is equal to 8, x2 is equal to 18, and x3 equal to 0 is 70, which is the optimal solution or the minimum value of the objective function. Now again, if you try to call what is pivot column, then it will say that all reduced cost coefficients are non-negative, therefore you do not need to proceed. And as I said, in this case, what are the basic variables now? The basic variables are x1, x2, x6, and then we can so here I have just written what is the solution, because these all reduced cost coefficients are non-negative. Therefore we have reached the optimal solution, and the optimal solution is equal to 70. The value of the objective function here z is equal to 70. So it should be z is equal to 70. That occurs at x1 is equal to 8, x2 is equal to 18, and x3 is equal to 0. That is how you can solve this problem by employing step by step this simplex algorithm. Right. And on the way, in case we have somewhere where all the coefficient in the incoming column are negative, then we know that the problem is unbounded. So that we will look at some other examples little later. But now let us look at how we can solve this problem using inbuilt function in Sage. Inbuilt function in Sage. So at present what we have done, we have created our own user defined function to do each step. That is each step in the simplex algorithm, which is how to decide incoming variable, how to decide outgoing variable, and then how to pivot. So all these three user defined functions we have used. But Sage also has another inbuilt function which is called interactive LP problem, which we also used in case of 2 variable. Now let us again use this in case of 3 variables problem. So this is again exactly the problem which we are defining. So A is the rows of the coefficient matrix A, B is the right hand side, C is the coefficient of objective function, and create P is equal to interactive LP problem, give the A, B and C, and then the variables here are x1, x2, x3, x4. The problem type is maximization. Then the constraints are all less than equal to type. So less than equal to, less than equal to, less than equal to. In case some constraints are greater than equal to, you have to, or equal to, you have to change accordingly. And the variable types are all non-negative. So that is the problem. This is how we would define the problem. This particular facilities like interactive LP problem is going to be more of pedagogical benefit. This will also tell you how to solve the problem step by step. Okay, so now we will convert this problem into standard form, and then let us ask it to show what is, let me show what is P. You can see here, this is the problem, which is exactly what the problem we have started, right? Okay, so this is the problem in standard form. Now this problem in standard form I have considered is equality type all constraints. But here in Sage Math, the standard problem they will consider of maximization type and all less than equal to inequality. Okay, so right. Now what we need to do is we need to run what is called simplex method. So P dot run simplex method, when you apply, then it will create a sequence of steps, and of course it will write in compact form. So the first one is you can see here, they are the first x4, x5, x6 was basic variables. This is the row corresponding to reduced cost coefficient, the last row. Of course, since here the standard problem is maximization type, they will not take the negative of the coefficient, but rather it is the coefficient itself. And then you look at whether all these coefficients are negative. In case all of them are non-positive, then you have reached the optimal. Here in this case, you will take the smallest of this coefficient, which is 2. So this column corresponding to 2, which is x1, becomes the incoming column. And then take the ratio with the positive one, and then here in this case, this x4 will be outgoing, and then you need to again update this. And so here you can see here x1 is entering and x4 is outgoing, and then do the next step, which tells you that x2 is entering and x5 is leaving variable. Then when you update this again, then you have x2 is entering and x5 is leaving variable. When you update this, okay, now you can see here the value of the objective function is 70, and all the coefficients here have become negative or non-positive. So that is where you can stop. So that this though in our case we consider standard problem as minimization type, here in this standard interactive LP problem, this Sage has considered the maximization type of problem, and then it has done these steps in somewhat compact form. Okay, so here it says that the optimal value is 70, and that occurs at x1 is equal to 8, x2 is equal to 18, and x3 is equal to 0. Now this actually in Sage Math, the implementation this implementation of these steps are similar to the steps that is given in this particular book, which is titled as Linear Programming Problem Foundations and Extensions by Robert J. Vander Bey. This book is available online, so you can look at this particular book and go through the algorithm on simplex method. Okay, so sometimes I found that this, when you run p.run simplex method, this display may not be proper. It may not look like the way I can see here. So in that case, that problem can be taken care to some extent by this particular set of codes. So in case you find that this is not displaying the steps properly, maybe you can try this particular code, which is in this case what we are doing is we are converting this p.run underscore simplex method into string, and then some kind of markdown package, the display from the markdown package, IPython package is used here. So let me run this. In this case, again it will display the same thing in my case, but you might be able to resolve in case you don't see this display in proper format. Okay, fine. So let me stop here. In the next class we will look at some more problems, so that this algorithm will become much more clear, and then we will also make use of another inbuilt method in Sage Math, using which we can solve linear programming problem. This interactive linear LP problem, in this case interactive LP problem, this, as I said, it is more for pedagogical purpose. So if you want to solve this more efficiently, there is another inbuilt method which can be used, and that we will look at it in the next class. We will also look at more problems which could be unbounded or which may have alternate solution. Okay, so let me stop here. Thank you very much.